Right, we are back. I think we are back in business. Good. So now let's consider regressive models for binary traits. So in S.A.G.E 4.0 and above, we have available a multivariate logistic likelihood retaining correlations of order 2 only. Okay. So for a pedigree comprising K individuals, you product from K from I going from 1 to K. This we use a logistic function. I think that comes up. Where am I? Whoops. Yeah, we use a logistic function, and I don't see, I thought I had that. And it turns out to be something like this. It's very complicated, but you multiply this by this. This is for a first order correlation. So if we look at a nuclear family, this becomes for the mother, father, and the C children. You have the, first of all, the mother, father. I'm going to get rid of this. I don't know. Oh, Lordy. I wish people wouldn't call me. You have here the correlation. This one here, this is a correlation for these, and this correlation in this particular case for a nuclear family, you have one for the mother and father, you have one, you have the father, offspring, mother, offspring, sib, and I've got the father, mother one here. Anyway, everything's on the logit scale. So this theta, this theta is a mean, well, on the logit scale though, this from baseline genotype parameter plus all these covariates and things, and you can estimate the covariate coefficients. Now, this was, if you want to see more detail about this, you look up the paper of Karanarate and Elston. And it's, if you read that paper carefully, you'll find there's problems with these correlations. So I would suggest this is a good model if you want to have covariates in this heuristic model, but only if you assume no familial correlations. These are the residuals, they really measure residual association, and they can be converted to correlations by this, this formula here. So the point is, you have to say, if you've got covariates, well, S.A.G.E outputs the correlations of average values of all the covariates for the class of relatives involved, both overall and genotype specific. But I would strongly suggest you do not use this model if you have familial correlations. It's fine if you just want to put covariates in and you want everything on the logistic scale. That's fine. So for extended pedigrees, we use the regressive model class D assumption that conditional on the major genotypes or phenotypes of the parents and all SIBs in the same ship, the phenotypes YI and YJ depend the phenotypes Y on any two pedigree members are independent. The class A model is not available. We used to have it available, and the reason why it's not available, it has lots of problems with it. I didn't realize till I looked into it. Under some circumstances, you have to have a negative mother-father correlation, which didn't make sense. But the disease prevalence can be constrained, and we'll talk about that later. So if you do want some familial correlations, use the finite polygenic mixed model. In other words, instead of having an infinite number of polygenic loci, you have a finite number, such as 2, 3, 4, or 5, maybe. So in addition to the major genotype, we assumed K additive diallelic polygenic loci. Typically, I will use 3 for K. And then if we found empirically that once K is 3, it doesn't make much more difference. They're likely to go to 4 or 5, but you can if you want to. The alleles are A with effect alpha and B with effect beta, and the allele frequencies P and 1 minus P. These are for these polygenic loci. There's a finite number of them, but they're going to imitate a polygenic model. The polygenic effect is the sum of the effects of the alleles at all K loci. And if the pedigree member has VA alleles and 2K minus VB alleles, remember there's 2K alleles altogether when there are K individuals, the effect is what we call mu V. It's V times the number of A alleles plus 2K minus V, sometimes the A allele effect, and 2K minus V times the beta allele effect. So alpha and beta are automatically chosen to make the mean polyg effect 0, which means that alpha is equal to minus beta when P is 0.5. And V is the polygenic number. Now, when we did this, I said, well, why don't we let people put different values for P? As far as I know, nobody has ever put in P anything but 0.5. I don't know what difference it would make. It would make your polygenic number, the polygenic effect, it would skew it one way or the other. I'm not sure there's any need for it, but you can, in fact, change this P if you want to. I've never tried it. So we assume that, conditional on the polygenic numbers of the two parents, VF and VM, the polygenic number of any pedigree member is independent of the polygenic members of all the other pedigree members. In other words, we can write it in this form. This for the founders and the non-founders, they're just assumed to be independent. Now, this allows us to use the Elster's algorithm summing over 2K plus 1 possible polygenic numbers for each individual. And if you've got 3 major genotypes, over this times 3. Not outlandishly large number. It can be done. Now, this is strictly not consistent with Mendelian inheritance, but does lead to a conditional correlation of 0 between polygenic numbers of any 2 pedigree members. So all I can tell you is it works, and it seems to give what I consider good results. The user can specify the number of polygenic loci. The default is 3, and also the allelic frequency P, the default is 0.5. I've no idea what will happen if you change P. Somebody should try it sometime. Certainly, once you've used 3, you can, right at the end, when you've decided on a decent model and everything, you can try 4, and my guess is you'll find very little change. As you will recall, once you have polygenic, if you remember when we talked about polygenic inheritance on day 1, if you have 3 additive loci with equal allele frequencies and equal effects, that's pretty close to a normal distribution. So you can't have residual correlations in the FPMM. You just got what you've got. As for the regressive models, the mean and residual variance can depend on covariance. The penetrance function is now a function of the polygenic effect. For a continuous trait, you see you just have this you just have this normal distributed U with, but now it's got this added on this mean of the polygenic number, and you have some variance. For a binary trait, we do everything on the logistic scale, where theta is now this major gene effect plus a polygenic effect plus say Xi1 times covariate 1 plus Xi2 times covariate for the particular individual. So we discussed variable age of onset models before, and I'm going to repeat some of what I said, but I'll be a little bit extra this time. So we denote the age of onset A with density FA, and cumulative distribution is the probability of having been affected by age A primed, capital FA primed, okay? And if you'll remember, we assume that once affected, always affected. The problem, people say, well, why don't we use survival analysis? The problem with survival analysis is that the susceptibility is required to be 1. Now, you might note also, because we're assuming a logistic distribution, or cumulative logistic, or a cumulative normal, that in theory you can have negative ages of onset are allowed, but if you think about it, it should be pretty good, because when they're negative, those probabilities or the likelihood is going to be pretty small. We'll see a picture in a minute. So we define the susceptibility to be the probability of ever being affected. And it doesn't have to be 1 as in survival analysis. It is whatever you want it to be. And we can often describe approximately the same population with respect to this probability in 2 quite different ways. So look at this. We've seen this picture before, and you can see up to age 100, they're pretty close. Once you get past 100, they're completely different. This, you can see there, what this is, this has a complete gamma equal 1. Normal distribution would mean about 110, variance 15 squared. This one, gamma equals to 4, and the age of onset is a mean of 95 and variance 10 squared. So you can see these two look pretty close. And up to age 100, then they go way off. And these distributions, of course, can go negative way over here, but the likelihood there is going to be so small that it won't matter. All right. So we are accumulating up to these points. And I say all the negative stuff is basically 0, even up to about here. Okay. Thus, for a random person from a particular population, the appropriate likelihoods are as follows. It's gamma FA for an affected individual person, affected person with known age of onset A, and gamma capital FA prime for an affected person with unknown age of onset, age of examination A prime. All right. It's 1 minus this for an unaffected person with age at examination A prime. So when these functions are made genotype specific, they're interpreted as penetrance functions. They can also be made covariate dependent. Gamma can and the A can. In particular, the mean of F and the susceptibility gamma can each be made dependent on covariates. So the penetrance function consists of 2 parts. Susceptibility, we use the logit. And for age of onset, is also assumed after transformation to be a logistic density function. We always think of the logistic as the cumulative logistic. These are what people think of, but there is also a logistic density function, which is almost identical to, I say almost identical to a normal density function. They look pretty much the same once you standardize them to have the same mean and variance. The logistic density function is very similar to the normal density function. That's what I just said. The mean can depend on covariance, the variance can depend on the mean. Years and years ago, we actually, and we published a paper in which we used a logistic density and also we used a normal density, and we found basically exactly the same answers, whichever we assumed. This was for a quantitative trait a long time ago, and I don't remember, I think it was one large pedigree. Anyway, the cumulative logistic allows interpretation of the parameters log odds. That's why we use logistic rather than normal. It's much easier to interpret the parameters if you use a logistic here than if you use a normal. Okay. The logistic distribution, most people know the cumulative logistic. That's when they use logistic regression. This is what they use. And but if you take the derivative of this, you get the density function, and this is what it is. The mean is minus beta over alpha. The variance is pi squared over 3 alpha squared, and the standard deviation is this. So if you have the beta and the alpha, which is what you get out of the logistic distribution, the beta and the alpha, the mean is just that, the variance is that, standard deviation that, and the distribution will look very, very much like a normal distribution. However, so alpha is the age coefficient, beta is the baseline coefficient. As for any other quantitative trait, the mean can depend linearly on covariance, and transformation of both sides is performed by default. You don't have to, as I'll mention later. However, the transformation, and I didn't say earlier on, did I? I think if you had only a logistic, if you only had a affected, unaffected, no age of onset, it turns out that you do not, what am I trying to say? It turns out that you do not, in that situation, have to worry about transformation. Transformation at that point is unnecessary. If you have a binary trait in and you assume that it is logistically distributed, then you do, and with you just don't have to worry about transformation. And that was a paper that came out about 10 years ago. Very interesting paper. So, but the point is that if we use the logistic distribution, it has the advantage that we can interpret the parameters can be interpreted as increases in log odds in the susceptible population. It would be the whole population if the susceptibility were 1. So in other words, we have the probability affected by age A prime given you're susceptible in your susceptible population, in the susceptible, is this. This is the cumulative logistic, which you're probably all familiar with. And so the odds of being affected by age A prime given susceptible, you just you take this P, substitute in, and it's this simple e to the beta plus alpha A prime. A prime is the age of aged examination. Thus, the log odds of being affected by age A primed is the log of this, in other words, just beta plus alpha A prime, which increases by alpha for each unit, in this case, year increase in A prime. Now, suppose the log odds for a person with genotype G is beta G plus alpha A primed. Then, for susceptible persons of the same age, the increase in log odds for carriers of a dominant allele, we assume it's dominant, it's going to be beta A prime minus beta B prime. Okay, because this bit disappears. Okay, so that's really rather neat. Susceptibility, we assume, as I said, a logistic distribution. And if there's a major gene present, this baseline the effect of the major gene will go into here, the polygenic effect here, and then you may have covariates. In this case, I call the coefficients of the regression coefficients on this, I call them omegas, just for lack of knowing what other Greek symbol to use. So are there any questions up to here about what we do for age of onset? And no questions? Then we shall continue. We shall talk about ascertainment. We talked a little bit about it on day 1, I suppose. We have to talk about the proband sampling frame. So it is defined independent of the phenotype. Is the catchment area where you're going to go and get your probands from. Probands, or what we might call proband combination, whatever. It's where you're going to catch people. Unfortunately, it must be known for appropriate ascertainment correction. Right? The sample pedigree has 3 parts. You've got this whole big pedigree. There's 3 bits to it. There's the probands or proband combination. For example, you may select a family because two SIBs are affected. That would be what I call a proband combination. Other people will call them 2 probands, but they're not probands because they're not independent. And if you'll remember, by the WHO definition of probands, they are independently ascertained. There are other members who are in the proband sampling frame. And then there are other members who are not in the proband sampling frame. Those are the 3 parts. So, first of all, what do you mean by a true pedigree? We somehow assume that these true pedigrees represent, this population of true pedigrees represents the population under study. Okay. And in these true pedigrees, we assume all the founders are independent. If not, the pedigrees aren't big enough. You should have gone further back. Even, you know, even if you don't have values on them, they are related, and you should, because of earlier connections, and they should be there. I suppose there's no point in going back more than 3 generations, maybe not more than 2. But you are assuming that all the founders are independent. The members of a true pedigree can be classified as belonging to the proband sampling frame versus not belonging to the proband sampling frame. They can be sampled or not sampled. In other words, you have them in your sample or they're not in your sample. The proband sampling, the proband sampling frame members of a true pedigree who are not sampled, they cause problems in the case of multiple ascertainment, not in the case of single ascertainment. But in the case of multiple ascertainment, they are the problems. because you don't know them. They're not sampled, so you know nothing about them. You need to know their places in the pedigree and their phenotypes. And if they're not sampled, then you don't know their phenotypes. All right. So Ginsburg did a lot of simulations imputing pedigree-specific mean phenotype values, and he found in one of two cases, he found the biases of just imputing the pedigree-specific mean for those individuals gave results less than one standard error. Now, the paper by Ginsburg here, I have a note here that suggests it's nearly impossible to read. It's better to read the book that came later, but I've got to warn you, the book is not easy to read either. Probably more precise than the paper, which I have a note that it's completely incomprehensible. Ascertainment age of onset. We assume age of onset and age of examination are independent. Well, let us assume that anyway. If we assume that, then we can condition on that person being affected at age of onset A, or preferably on that person being affected by age A prime. Okay? That's if we can assume that the age of onset and age of examination are independent. Now, let us assume the age of onset and age of examination are highly correlated. Then it's safer to condition on becoming affected at age of onset A. Remember, the independence refers to the population of susceptibles, which is not easy to test who's in it and who's not in it. And there's a problem if there's a correlation and age of onset is not known. So the point is that if you condition on at age of onset, you are conditioning on more, and so you lose information. But if you condition on at, it's safer. But sorry, that's what I said. If you condition at, you lose information. You'd like to say by, but you can't. And this is a question of the two principles that we talked about, the principles that you want to condition on as much as possible. And if you condition on more than is necessary, you lose information. So any questions now on the, as we mentioned, I remember on day one, you only allow certain models because, you know, you can't allow the age of onset and the susceptibility both to allow on anything you want. I mean, you can try, but the thing would blow up, so we don't let you do it. Any questions? Well, I suppose the main question that I will pose for you is, what do you do if you don't know the age of onset? Well, typically we assume that the age of diagnosis is the same as age of onset. Or you may be able to say, well, we know that the age of onset typically is 1 year less than age of diagnosis, or 6 months less. And you could do that. But the model itself is assuming age of onset. But in practice, you're going to interpret it as age of diagnosis if they're highly correlated. Hearing no questions, we will continue. Relationship testing. I think I've already gone through a lot of this, but we'll do it a little bit more now. There's a Markov process method used by REL test. In spirit, it's an extension of the identity and state methods in that one sums over markers, but it uses identity by descent and takes into account correlations among markers. That's the main thing. It uses the whole genome and it uses multi-point computations. It generates absolute measures of relationship, gives you nice histograms, and it's close in power to likelihood methods. This was all due to Jane Olson, 1999, and as some of you know, she died relatively early at age in her 50s. Really sad, because she did all this nice stuff, and as we'll see later on, she did other stuff that I'm sure she would have corrected the flaws in what she, I say flaws, we'll see later on what assumptions, unrealistic assumptions you're making in other programs. But for REL test, it's a beautiful program. We have a Gaussian process model. The ideal infinitely dense, fully informative process along a chromosome is what it looks at. So let XJS, and that's 0, 1, or 2, be the number of alleles shared identical by descent by the pair J at a point S on the chromosome. And we are basically going to assume that this thing is a continuous Gaussian process model. So this is what it really looks like. This XS, as you go along, it's going to have crossovers. I wish this thing wouldn't keep popping up. Go. There. If anybody knows how I can stop that popping up, let me know. I've no, it keeps coming up and I don't want it. Google wants too much. So you have where the arrows are crossing over, and you can see this thing fluctuates about 1. From it's sometimes 2, sometimes 1, sometimes 0. So look at a set of N Sib pairs. Let XS be the total number of alleles shared identical by descent at location S for a set of N Sib pairs. Then if we take XS, take away N, which is its mean value, divide by N over 2, the square root of N over 2, which is the variance, then this ZS becomes normally distributed asymptotically with mean 0 and variance 1. When N is equal to 1, then you've just got XJS minus 1 over a half to a half. And the expected value of this ZS for various relative pairs looks like this. And that is, you have the unrelateds are very small, cousins not quite as small, half sibs again not as small. Full sibs and parent offspring have a mean of 0, and MZ have a very large value for this. And this, in a way, this, what Jane also did, is you can compare it with what Emily Feingold did. What she did was she assumed an infinite number of pairs, whereas Jane is assuming one pair averaged over the whole genome, lots and lots of positions over the whole genome, but it's in spirit very similar. So what are the features of this? It's full multipoint. It uses all marker information. It needs you have to input GenIBD output. It has only one multipoint calculation required, which is really amazing. A test statistic YJ is valid against all non-SIB alternatives, but has no power to differentiate between parents and offspring pairs, differentiate SIBs from parent-offspring pairs, full SIBs that is. And it's sensitive to decreased marker informativity. I think we've seen this. We saw a slide about that. Or maybe we'll see it later on again, but we saw it on the first day. So consider a SIB pair and a single chromosome. For a chromosome K of length LK, what we do is we take these ZJs and we integrate them over from 0 to the whole length of the chromosome and divide it by 1 over LK. Then the expected value of YK is 0. And it turns out that the variance between 2 is 1 over L squared. And you've got to get this integral from 0 to K, LK, double for ZJR and Z for 2 of these. And it turns out, and I don't remember all the details, I'm sure they're in her paper, you get this expression here, where beta is a covariance parameter that turns out to be full sieves 0.04. Consider the whole genome. Then what we have then is we get this Yj, and it tends to be normally distributed with mean 0, variance 1. And as the length of the genome increases, number of chromosomes K, as you get more, then you get it going towards normality. As I said, what Jane does, she looks at one Sib pair and averages over many of them. No, she doesn't. She takes this one Sib pair and averages over the whole genome, or as much as you wish to do. In practice, she points out, only a few chromosomes are needed for the asymptotic approximation of normality to hold. You don't need many chromosomes, but, and this is the important thing, you need at least half the genome if you want accurate relationship estimation. That is what Jane Olsen suggested. So let's look at what happens with real data. What we do is we compute this estimate of XJS at 2 centimorgan intervals across the whole genome. And this XJS is the probability that Sib pair J shares I alleles identical by descent at locus S. In other words, it's the probability, it's estimate of sharing 1 plus twice the estimate of sharing 2. And so this is what it looks like. Now, these are where you maybe have data, but what you're looking at maybe every couple of centimorgan intervals, and if they're close enough, you really have a continuous distribution. So this is where the tight marker arrows, this is where the location of the tight markers are, but because you're doing multi-point, you basically have a smooth curve. And you infer the IBD sharing at locations of markers, for example, every 2 centimorgans. And then you have this curve here. And what you do is you approximate it, the area under the curve, by using rectangles. And in particular, it's very accurate if you use Simpson's. Some of you may know Simpson's method, or I don't know whether it's called Simpson's method, Simpson's rule. It's remarkably accurate. So this is the true Sibs will be 0 here. This is the ideal situation. The half Sibs will be way over here. But what happens in actual fact is that you get decreased marker informativity. Okay. Anyway, but it still has a mean of 0. This assumes that all your assumptions are correct. The problem is that the optimal critical value for determining, if I go back, let me go back, you want a cutoff about here so you can know the difference between half Sibs and true Sibs. But that optimal critical value depends on marker informativity. And what Jane did, she obtained optimal critical values empirically as a function of the log total genetic distance divided by 150 t, because that was what she simulated, 150, and log average marker informativity. This is the Lander and Kruglia average marker information content. And she found out to classify SIBs and half SIBs, this is what you do. She found that by a lot of simulation. So consider parent-offspring pairs. We already know that they always share exact. So I think this is where we were. I'm not sure exactly. So YJ is not useful for distinguishing parent-offspring pairs. So what we look at, we now look at the, we look at the, we have this, this is one if pair IJ shares one allele identical, well, this one is 2 here, probably they share 2, minus the probably they share 1. 2 plus 0 minus 1. Okay, and that works. I gotta, that's fully, for fully informative pairs, this has a mean value of 0, and the parent offspring is minus 1. So we estimate this in the same kind of way, and we do everything similar. Did we, but now the we have 0.08 instead of 0.04 is the value of beta. And then we allow for data errors. What we do there, this is rather neat. And I would have done some kind of Windsorizing, but Jane found this. You adjust the cut points if the SIB pair histogram is not centered around 0, and she tests whether a shift is present. And to do this, she estimates the shift using L2 robust estimation, which I know very little about, but it's rather, it's in this paper here that you can see, Scott and Susceptibility. And you can see you maximize this quantity. And where phi is a normal density, it's similar to, I think it's similar to Windsorizing, getting rid of things in the extremes, but it finds a basically a big mass, and it maximizes at the right. So now you adjust the cut point. You take a new cut point equals the old cut point plus the mean, repeat for the parent offspring statistic, and you perform classification with new cut points. And you can test whether whether the mean is in fact the same as it was before, and you get a confidence interval. And if 0 is not included in the interval, then the SIB pair histogram is not centered around 0. But as we saw on the first day, it might be significantly different, but it may not have big effect on these statistics. Okay, oh, we're all ready for lunch. Wow, what time is it? It's 12:09, and we weren't supposed to. Oh, wow, we're early, aren't we?
Yes.
Yeah. I didn't realize. I must have gone very fast. Any questions about that? I'm sorry for all the interruptions, but even with them, we seem to have flown by. Let me go back to this. We didn't have lunch yet, did we? No, we had a break. I'm getting very confused these days. No questions at all about all of that? Well, yes, question?
I actually have one question on the well test.
Yeah.
Okay, how well this method would work with the SNP data? Does it matter? Because I remember this was with the the microsatellite data.
Oh, I think it works well with SNP data. I don't know, but I think it works well. I think it does because you have so much data. And remember, it's all going through GenIBD.
Actually, no, the REL test actually does calculate its own. It doesn't go through the GenIBD.
Then I'm wrong. Yeah.
Yeah. I mean, it's a full multi-point, but it does do the multi-point calculation, assuming, I mean,
Yeah.
how can I say? Yeah.
Yeah, I think you're right. In fact, the whole point is it's very fast. It's very
Right.
fast.
Right.
I can't think that with SNP data, it would be, I mean, what you might want to do with SNP data is have them close together. But the other thing you could do, though I don't think it's necessary, we shall talk about haplotype analysis later on. You could get haplotypes and put those in, but I don't think that's necessary at all. I think it'll work well with SNP data.
Okay. The reason that I am asking is like that, with the microsatellite, and also this one is using the genomic, like genome map, not the physical base position information.
That is correct.
Multipoint itself is actually using the genetic map distance, not the
right.
I mean, we can do the approximation from the base position to the genetic map, but,
yeah, but
I'm asking whether that itself will be actually affect the result of or the validity of the test that it's doing in well test.
Well, I suspect it would work okay for the simple reason that you are going through this business of what I think amounts to trimming and finding a better mean. I think it would work. I mean, I don't know. I can't guarantee that. But my guess is it would work. A lot of these things have not been tried. I would suggest, by the way, to everybody that if you try some of these things, we have the open source S.A.G.E. People can report things there, and they can even change the programs if they want to and get new better versions. I mean, this is all possible. I know sorry, Joan.
One of the practical issues with any of the multi-point and multi-point approximations is how well do they deal with markers that are in LD with each other when we're assuming in the underlying method, you're assuming no linkage disequilibrium between the markers. Correct. And so for most things, we've found you really need to trim out the intermarker LD.
Right. You wouldn't you wouldn't want to have all the SNPs if they're a lot in LD. That is true.
Right. And so what we've done in practice with most linkage methods is first we'll go in and just say, okay, drop every SNP that doesn't have a minor allele frequency of 0.4 or better, 0.4 or higher. So that you've got your most informative SNPs, and still you have too many. And then we use something like Plink or HaploView to start trimming out some of the LD until we get to, you can usually get it down to maybe 1 centimorgan between your markers and get most of the LD out. We also tend to do 2-point linkage when we have really dense maps, because then if we find that there is a region where the 2-point scores are high, then we look at what are our very high LOD score markers in that region, and we make sure that we pick at least one of them for the multi-point map, and then get rid of LD around them. And that seems to be the most powerful way to deal with these incredibly dense maps.
It makes a lot of sense, Joan. Thank you for adding all that.
And Merlin says that it can deal with intermarker LD, but not this much intermarker LD. So even for something like Merlin that is saying it adjusts for intermarker LD, you still have to trim some, because if you've got, 1,000 markers in a little bitty space that are all in really high LD with each other, even Merlin's approach to adjusting for the intermarker LD just falls over and dies. By that I mean it has too many false positives.
Yeah.
So you've got to do some trimming.
Yeah, that makes a lot of sense. Thank you, Joan. I've been out of this for so long now that I haven't kept up with using S.A.G.E with the modern kind of output one has.
Right. And this is not just S.A.G.E. This is any linkage method that is multi-point.
Right.
Because they're pretty much all assuming that there is no intermarker LD. So you have to deal with it for any of them. And so we always, when we have dense marker maps, we do 2-point first and see what it tells us. And then we also try and do some multi-point to make sure that what we're seeing makes sense, see if we get any better localization of our peaks, all of those things. And of course, when you're dealing with SIB pairs, having multi-point really helps you a lot.
Right.
But that process of trimming out the LD is not trivial.
Sure.
Yeah.
That makes a lot of sense. Thank you.
Yeah. We all sort of wished we could still get those microsatellite linkage panels because they were so informative, and then maybe supplement with a few SNPs. And for some of our older studies, that's exactly what we do. We merge our old microsatellite maps with new either SNP or sequence data and merge them together into a merged map, and therefore get the best of both worlds. We have more coverage in between the microsatellites, and we can just put in enough variance in between that there's not a lot of LD. It sounds simple, but it takes a long time. I see Ju shaking her head yes to everything I'm saying.
Let me ask you.
We've all done this, right? You and Ju?
Yeah. Let me ask you something else, John, if I may.
Yeah.
Supposing all you have is this SNP data, and I don't know how difficult it would be, but do you think it might be worthwhile trying to find haplotypes and using those
exactly. And that was why I was kind of excited about when we talked earlier about doing the family-based haplotyping, because I really think that will be helpful in some of our families where we have SNP or sequence data, and we have a really strong region that shows linkage with our 2 points, where you just have this line, essentially. When you plot the 2 points with little bars for each SNP, you just see a line. It's so dense, and they all have the same log score. And trying to do multi-point there and to trim out the right things is problematic. It'd be really intriguing to do the haplotypes. And one thing we often see is different haplotypes in different families. So being able to do the haplotypes in a region where several families are all linked to the same region, and then say, well, what variants are actually on the linked haplotypes in family 1 versus family 2 versus family 3? Because in some of our lung cancer things where we've got linkage to the region, we're actually seeing like not quite all overlapping haplotypes. So there seem to be 3 distinct linked haplotypes in different subsets of families. So it may be that we have actually 3 different causal genes that all just happen to be close to each other. And in the original microsatellite multi-points gave us 1 peak. But when we really drill down, we're kind of thinking we've got maybe 3 different genes going on here.
Yeah, you
So
might
this
well
is where
have.
the haplotypes are going to be so incredibly useful.
Sure.
Yeah.
All right. Let me
It's
see.
fun stuff. It's keeping us busy.
Now, we were supposed to start again in about an hour's time. Is that right?
Yes, we start back at 1:10.
1:20. 1:10?
1:20.
1:20. Yeah, 1:20. Now, I'm not going to touch this computer at all. I'm just not going to touch it. I'm not going to look at my email or anything. So, Yunju, I shall just leave it where it is. And when we come back, I hope it'll work at 1:20. Okay. Thank you, everybody. You have a whole hour for lunch. That's good. And I shall see you again at 1:20. Thank you.